طيب okay, شباب, let's start today's class. Last time we started this chapter, actually we talk about, just to give a brief about the refining process and the production of the different fuel and the most common types of fuel. Then we classify all of the fuel under the fuel families, and we have learned how to know actually the chemical structure of the fuel, the number of carbon atoms, number of hydrogen atoms in any fuel, and from name of the name of the fuel, the prefix and the suffix of the name, we can classify actually each fuel, and we know about its chemical structure. Also, we looked last time at the different properties of the general properties of any fuel. It can be applied for any fuel. We talk about the specific gravity. We talk about the flash point, the point at which actually we can have a flash of the fuel. And this is for the safety of the fuel. It has to be actually any fuel should be kept at a temperature lower than the flash point, in order actually to just avoid misfire or something, or starting any kind of fire in the storage tank of the fuel. Then we talk about some properties that are actually very important to the gasoline engine. We talk most importantly about the fuel volatility for the gasoline fuel. At the cold start, engine cold start, the fuel should be actually volatile at lower temperature in order actually to be able to supply the engine with the required amount of fuel to start actually the engine properly. This is, we call it the cold start. But the fuel, for gasoline should not be much volatile, because actually having more fuel to be volatile, actually more volatile at the engine cold start, the fuel actually will evaporate as the engine heat up, and this actually vapor will just block the fuel line when the engine is heated up, and causing actually what is called the vapor lock. So the vapor lock, in this case, actually we have the fuel is much volatile, have actually higher volatility, so that actually is volatile at lower temperature start, and as the engine actually heat up, more fuel is vaporized. So this vapor actually just blocks the fuel line and prevent actually the fuel to be passed to the engine at higher temperature when the engine actually just heat up. We talk also, and we said about actually the vapor pressure. The vapor pressure is the pressure at which actually some fuel vapor is created. We need actually to keep the engine with this vapor pressure should not be actually greater than 0.7 bar, in order to make sure that the fuel will be volatile enough at the engine cold start. This pressure, vapor pressure, should not be actually fall below, actually should not be greater than 0.7 in case of the summer fuel, and in case of winter it should be a little bit raised due to the cold weather in this case, in order to make actually to make sure that the engine is supplied actually with the correct amount of fuel at the engine cold start. But this vapor pressure, شباب, should not be actually below a certain value, because if the vapor pressure is very low, that means actually more fuel will be evaporated at the engine cold start, and it will cause actually what we call the vapor lock. We said last time also that some engine, there are some fuel additives, mainly alcohol. Usually we add some alcohol to the fuel in order to improve actually the fuel quality and the resistance actually to the self-ignition, and the resistance actually to what is called the fuel knock. So in some cases we add alcohol, but this addition of alcohol should be actually very limited, because alcohol is very volatile substance. So at the engine cold start, most of the alcohol in the fuel will be evaporated, and it will result actually in vapor lock. So this is actually one of the main reasons that we have to be specific actually when adding some alcohol fuel to the gasoline engine, especially at the cold start. Type, this is we stopped at this point last time. So let's continue today. Still we are continuing our talk actually about the properties of the fuel for the gasoline engine. Inshallah, today we are talking actually about one of the most important properties for the gasoline fuel, which we call it actually the octane number of the fuel. It is called also as the anti-knock quality. We call it anti-knock quality index. So the octane number of the fuel, شباب, gives us indication about the resistance, the ability of the fuel to actually to resist knock, or to resist actually self-ignition inside the cylinder at the end of the compression stroke. And that's why when you go to the gas station, you will find actually different grade of fuel. We have octane number 91, we have octane number 95, and we may have actually octane number 98. So the difference actually, as the octane number gets higher, this means actually this fuel is resisting actually the self-ignition, and this fuel actually does not result in engine knock. طيب, what is engine knock يا شباب? Engine knock actually occurs first of all in the spark ignition engine, where we have the fuel plus air are mixed. The piston is going down while the intake stroke, so it takes actually the fuel plus air down, and then we compress this air plus fuel during the compression stroke. While the compression stroke, the pressure and temperature gets higher, and before the piston reaches the top dead center, in this case the spark plug will initiate the combustion. We'll have a spark to initiate the combustion. And in this case, we call actually the combustion in this case as the normal combustion. This is actually the normal way we have combustion in the spark ignition engine. But when do we have knock يا شباب? When the knock happen? So usually the normal combustion when we have a spark. In this case, a spherical flame will be just generated. If you look here, let's say this is our engine. So this is the piston here, the cylinder, and inside the cylinder we have the piston. Let's say this is the intake valve, and here we have the exhaust valve, and here actually at the middle we have the spark plug in case of the gasoline engine. So first of all, the piston moves down to take actually the air plus fuel, and then it will be moving up to compress the air plus fuel. While the piston is moving up, so the pressure inside the cylinder will be raised, and in this case the temperature will be raised. Before the piston reaches here, the top point, we call it the top dead center. In this case, the spark will initiate actually the combustion. We'll have the spark plug here, so a spherical flame will start actually to spread inside this cylinder. So the gases will be expanded beside the spark plug, and it will be actually a pressure wave actually will be transferred through the whole cylinder until actually all of the fuel plus air is consumed actually inside the cylinder, and this spherical flame has approached actually the whole of the cylinder and it has completed the combustion. In this case, شباب, we call it the normal combustion. But in case of abnormal combustion, this spherical flame actually results in pressure wave. So in this case, the pressure actually will be raised near to the corner zone. We call it the end gas. So due to the initiation of the combustion from the spark plug, spherical flame will be generated. It will result actually in pressure wave. This pressure wave will raise the pressure inside the cylinder near the walls of the cylinder. We call them actually at the end gas. If this actually pressure gets higher enough so that the temperature is exceeding the self-ignition temperature while the compression stroke, in this case actually another flame will be initiated here, and we'll have also another pressure wave. If this continue actually, and before the flame initiated by the spark, before it reach actually the end gas here, the temperature gets higher than the self-ignition temperature, so in this case another flame will be generated here, and another initiation of a third pressure wave, and so on for different point inside the cylinder, usually very close to the wall of the cylinder. If the temperature exceeded the self-ignition temperature before the initiated flame by the spark plug reaches this point, so in this case another flame will be initiated at this point. So it's a kind of successive flame or successive explosion. We call it actually detonation in this case. So this successive self-ignition result actually in the phenomena which is called actually the engine knock. So in this case actually we'll be hearing the engine is knocking. We have some noise from the engine. This noise is coming actually from the successive self-ignition inside different point inside the cylinder due to actually the increase of the temperature higher than the self-ignition temperature in this case. So in this case, if we have lower quality fuel of lower octane number, then in this case during the end of the compression stroke, the fuel actually will be self-igniting before the spherical flame initiated by the spark plug reach actually the end gases close to the walls of the cylinder. Okay, is this clear, Shabab?
Yeah.
Yes.
So do you have any question So this is يعني an idea about the knocking, the mechanism actually how the knocking occurs inside the engine. So usually we have flame is initiated by the spark plug. This flame just spread inside the cylinder while the compression is strong. But this flame actually result in pressure wave. When you initiate combustion, so pressure will get higher and the pressure wave will be just created inside the cylinder. This pressure wave will raise the pressure close to the wall of the cylinder, and in this case the temperature will be raised in this case. If the fuel يا شباب in the end gas zone here close to the wall is resisting of higher octane number, so it is resisting self-ignition, so it will not self-ignite. So in this case, it will be waiting until this spherical flame reach actually the end gas, and this is what we call the normal combustion. But if the fuel is a flow-grade fuel, low octane number, that means actually it will not be resisting the self-ignition, and the fuel actually will self-ignite before the spherical flame initiated by the spark plug approaches the end gas. And in this case, we'll have knocking because we will have successive self-ignition inside the cylinder, and this should result actually in the abnormal combustion phenomena, which you will call it actually the engine knock. But what are the effects of engine knock, Isabel? It will result in pressure spikes, pressure waves inside the cylinder. Those pressure spike will be approaching the piston, and this will hit the piston. It will just exert actually large localized force at a small area. So in this case, actually, it will cause actually piston vibration. And this will result actually in some knocking noise in this case. And that's why we call this phenomena as the engine knock. Because this pressure wave, we have several pressure wave due to the several combustion or self-ignition inside the cylinder. Those pressure wave or pressure spikes will just hit the piston, and it will create actually vibration of the whole engine. And in this case also you will have some noise as the engine vibrates. You will have in this case some knocking noise in this case, like when you are knocking a door. So it will exactly the same situation. The piston is just oscillating, vibrating due to actually this successive pressure rise inside the cylinder, and it will cause engine knock in this case. If you look here, Shabab, at this pressure crank angle diagram, this is the top dead center. Before the top dead center, usually the combustion start initiated by the spark plug. And actually, as the piston is moving up toward the top dead center, the pressure actually gets higher in this case due to the initiation of the combustion. If some knocking occur inside the cylinder, this will result actually in very high pressure peak. In this case, as you can see, this is actually when we have a strong knocking. The fuel actually is of lower grade, lower octane number. So we have actually self-ignition in this case in different location, and in this case we have a strong knocking in this case, and the pressure spike is very high in this case compared to actually the dotted line, which represents the case of the normal combustion. Okay, if we have some slight knock, and this is a usual practice in the car, you may have some a small amount of knock. In this case, actually, the pressure spike will not be that much, but still we have some pressure spike, and usually we try actually to minimize the knock to the minimum limit. But what else happen actually? In addition to this high pressure wave or high pressure spike, which cause actually the piston vibration and the knocking noise, also this spikes of high pressure will just hit the piston, and it will actually just penetrate inside the boundary layer. There is a boundary layer at the piston top surface. This actually boundary layer protects the piston against the high combustion temperature. So when we have those spikes, then in this case, this pressure spike will just actually penetrate inside this boundary layer, and the piston surface will be subjected actually to the high temperature in this case. So the high temperature will cause actually excessive erosion, and it may cause actually engine failure. As you can see here, Shabab, this is a piston that has been subjected actually for a long time to a strong knocking. So the piston area, as you can see, the piston is just totally destroyed due to actually the engine knock. So engine knock creates pressure peaks. Pressure peaks exist the force on the piston, so it can create vibration of the piston inside the cylinder, which causes the engine knocking or noise. And also it will result actually in high pressure spikes that will penetrate inside the boundary layer that protects the piston against the high temperature. And this high temperature will just actually cause erosion in the surface of the piston, and it may cause actually the failure. If you look here يا شباب, you can see the flame, the spherical flame is initiated by the spark plug, and this flame is spread actually inside the cylinder. And it will cause actually pressure wave that will transfer to the end gases, and it will raise its pressure. So the pressure will be raised, that means the temperature will be raised. If the fuel is not resisting the self-ignition, it will self-ignite at the end gases. The gases يا شباب close to the cylinder wall. The gas far away actually from the spark plug. So usually يا شباب engine knock occurs after the spark is initiated by the spark plug, and it causes high pressure rise inside the cylinder so that the end gas is self-ignited. So we have self-ignition at this point. We have another self-ignition at a second point, third ignition at a third point, and so on actually in this case. If you look at actually the top view, you can see here this is the main flame initiated by the spark plug, the spherical flame. It creates actually pressure wave, but in this case the fuel is a lower quality, then the fuel self-ignite close to the cylinder wall. You can see actually all around here we have flames that has been initiated actually before the main flame approach actually the end gases. And this is what we call يا شباب the engine knock. Is that clear يا شباب?
Yes, clear.
Doctor,
No.
how the fuel is resisting the self-ignition?
So شباب, usually any given fuel should have a self-ignition temperature. When you subject it to high pressure, its temperature will be raised. Then in this case, at a given temperature, this is one of the properties of the fuel. It will self-ignite. But usually for the fuel like the gasoline fuel, usually we add some additives like alcohols, bioalcohol like methanol or ethanol, or we can have actually some additives like benzol. We can add those additives to the gasoline fuel so that actually it will raise its self-ignition temperature. We don't need يا شباب the gasoline fuel to self-ignite because we have a spark plug here. Spark plug will initiate the combustion. This is unlike the case of diesel. In case of diesel, we need the fuel to have actually lower self-ignition temperature, so that when we just inject the fuel inside the cylinder in the diesel engine, it will just actually self-ignite and start the combustion. Okay, so usually we need the fuel in case of gasoline engine to resist the self-ignition, because this is the situation, as you can see, if the fuel actually is not resisting self-ignition in this case. It will result actually in engine knock, and the piston actually will be totally destroyed in this case, in some cases if we have severe engine knock. Okay. Type the sources of ignition يا شباب. Usually engine knocking occurs, as you can see here, when we have a secondary ignition source is initiating the combustion inside the cylinder. Secondary ignition source other than the spark plug, which is the self-ignition. But what are the causes of self-ignition in this case? First cause, or the main reason actually, is the end gas. The end gas actually, the temperature and the pressure of the end gas is raised after initiating the combustion from the spark plug, so that actually the fuel in the end gas region actually self-ignite. Another region يا شباب for the knocking or the self-ignition, or another source of ignition inside the cylinder, if we have some carbon deposit actually on the spark plug or in the intake valve, or in some cases if we have the injector is inside the cylinder, some new version of gasoline injection system, we inject the fuel inside the cylinder. So in this case, the injector will be inside the cylinder. So if we have some carbon or soot just actually due to the combustion just accumulated actually on the intake valve or spark plug, or actually for the fuel injector in this case, this carbon يا شباب is having actually higher specific heat ratio, have a higher specific heat at constant pressure. So it can absorb actually great amount actually of energy from the combustion process, and still actually it continue actually as a hotter body inside the cylinder, so that actually at the end of the compression stroke, while the pressure, after initiating the combustion, the pressure and temperature gets high, and this actually soot on the valve, accumulated on the valve or spark plug, will be just absorbing some of this heat, and it will be kept at higher temperature. So it can act as a source of ignition. So the valve itself يا شباب, if we have some soot or carbon deposit in this valve or spark plug, this will result actually as another or secondary source of ignition, so that actually it can result actually in igniting the fuel away from the spark plug. And in this case, we'll have another combustion has been initiated inside the cylinder. That means in this case, we'll have engine lock. And this reflects, Shabab, the importance of the fuel purity. We have to use actually a pure fuel so that actually we don't have soot accumulated actually on the intake valve or spark plug, because if we have such a kind of accumulation, this will result actually as a source of ignition for the fuel. So in this case, it will cause also the engine lock. And also, Shabab, the fuel in the end gas, knocking is characterized actually by the properties of the fuel in the end gas region, the ability of the fuel actually to resist auto ignition in the end gas region. So actually the fuel knocking is main function actually of the fuel properties, or what we call actually the fuel octane number. Okay. So the parameter affecting the knocking, Shabab, mainly we have the fuel type. The fuel has to be actually resisting the self-ignition inside the cylinder at high pressure and at high temperature. Also, another parameter, Shabab, affecting the knocking, which is actually the combustion chamber design, the clearance volume. If you remember, Shabab, we said, or what we call actually the compression ratio. We said the piston is moving from the bottom dead center to the top dead center. The volume here, we call it actually the displacement volume. And the volume between the cylinder head and actually the top dead center, we call this as the clearance volume. So here, Shabab, this is the displacement. This is the clearance volume, and we have actually, while the stroke of the piston, this is the displacement volume. And we have defined the compression ratio of the engine to be actually the cylinder volume divided by the clearance volume. The cylinder volume, which is the displacement volume, while the piston movement between the bottom dead center and the top dead center, plus the clearance volume divided by the clearance volume. So if the engine is designed actually to have higher compression ratio, then in this case we have to reduce the clearance volume, which is the volume between the top dead center and the cylinder head in this case. If it is low, then in this case we can raise the compression ratio of the engine. If we need actually to reduce the compression ratio, then we can increase the clearance volume. But as you know, in case of gasoline engine, they are limited actually to a lower compression ratio. We cannot raise the compression ratio in gasoline engine above the value of 10.5 or 11. Why we cannot raise the compression ratio, Shabab, in gasoline engine?
Because of the
we may export self-ignition.
Exactly. So if we design the Shabab, the gasoline engine to have higher compression ratio, that means actually the pressure, the clearance volume here will be reduced at the end of the compression stroke. This is the volume, Shabab, at which we compress all of the intake gases. We just compress to this minimum volume. So that means in this case the pressure will be higher and the temperature will be very high at the end of the compression stroke. That means in this case we might have actually self-ignition at different location inside the cylinder, and it will result actually in engine lock. And that's why in case of gasoline engine we cannot design the engine actually to have higher compression ratio. Okay. But usually, Shabab, don't mix it. Usually the manufacturer of any engine, gasoline engine, they design the engine at a given compression ratio that will not result actually in engine lock. So usually the engine is designed at a given compression ratio that will not result actually self-ignition of the fuel. This engine is designed to this case. And that's why the car manufacturer will give you a car, he will say, this car should be working with a fuel of octane number, let's say actually cannot be less than 91. Okay, at this compression ratio based on the design of the engine. Okay, so the engine is already designed not to have engine knocking. If you have engine knock, this is related to what? To the fuel properties, the octane number of the fuel. And the car manufacturer tell you don't use octane number below this value for this car, because actually the pressure at this compression ratio, the pressure at the end of the compression stroke will be this value and the temperature will be this value. So if you use this octane number or higher, it will not result actually in engine lock. But if you use the actually lower grade octane number at this compression ratio, design the compression ratio, it may result actually in engine knocking in this case. But usually engine knock is not due to actually higher compression ratio, because the engine is designed not to have actually knocking at this compression ratio. They have designed the engine not to have engine knock. But usually knocking occurs if we used actually lower grade fuel. So in this case, we initiate the combustion from the start plug, then we have self-ignition. So the sequence of events, we have the combustion is initiated by the spark plug, create pressure wave. It will help actually the self-ignition if we have lower grade fuel at the end gas zone. So with combustion initiated by the spark plug, then we have some actually knocking if we are using actually lower grade fuel. Okay. طيب if we have a شباب a turbocharged car or supercharged car, in this case we are using actually a compressor to compress the air in order to increase the amount of air into the engine. That means actually the intake pressure and the intake temperature will be higher in this case. And this actually raises the possibility actually that the pressure and temperature inside the cylinder will be higher, because actually we have higher amount of air is compressed actually in the same volume, clearance volume. That means the pressure will be higher in this case, and the temperature will be higher. That's why شباب the supercharged and turbocharged car usually they are assigned to work actually with higher octane number fuel. So if you have a turbo car or something, that means actually there is a higher possibility actually to have engine knock due to the high pressure and the high temperature inside the cylinder, because we have increased the amount of air using the air compressor, so the charge has been increased. So the pressure at the end of the compression stroke will be higher, and also the temperature. And that's why the supercharged and the turbocharged car are actually assigned to work for higher octane number. We prefer to work as a turbocharged car with octane number almost 95, okay? Unlike the case of naturally aspirated engine. So also intake air pressure and temperature affect the engine knock. The engine speed, the RPM of the crankshaft also affect the engine knock. I will be talking about this just right now, because engine knock can occur at lower engine speed, and also it can occur at higher engine speed. Also شباب the cooling water. We set self-ignition occur close to the end gas region, close to the cylinder wall, where we have actually the heat is transferred to the cooling water. So around this engine شباب here, in this around each cylinder, we should have actually some cooling water, and the heat is transferred here to the cooling water. But what will happen if we have some losses in the cooling water inside your car? Maybe we have some leak or something, or you just forget about actually the cooling water and it has dropped down actually below the required level. So what will happen in this case شباب? So the heat transfer from the combustion here to the cooling water, the heat transfer will be reduced. That means the temperature of the end gas city will do what? The temperature will be what?
Will be higher.
Will be raised in this case. Sorry, Ali?
No, I'm sorry. Go on, Doctor.
So in this case, شباب, if we have losses in the cooling water circuit, so the heat absorbed by the cooling water will be reduced. That means the temperature of the end gases close to the wall also will get higher in this case, and it may result also in self-ignition. And the excessive knock, شباب, if you have excessive noise in your engine of your car, this is actually the first sign that you are losing actually the cooling water in the cooling water circuit. And you have to check first if you have some noise in your engine like knocking. In this case, you have to remind what should be coming first to your mind, that I have lost actually the cooling water, and I have actually to check the level of the cooling water in the car. Because if the cooling water is lost, in this case the heat lost to the cooling water will be reduced, and we may have self-ignition here inside the cylinder, and it will cause actually engine knocking in this case. And most importantly, the parameters that are affecting the engine knock, we have the end gas temperature, the temperature inside the cylinder close to the wall, and this is actually the main characteristic of any fuel. It should be this temperature at the end of the compression stroke should be less than the self-ignition temperature of the fuel in this case. But what about شباب the engine speed? can we have knock at lower engine speed or higher engine speed? Which one has higher potential to have knock? At low engine speed or at high engine speed?
At high.
Do you think anybody else? Said, do you think that? So lower engine speed have higher potential to have engine knock or higher engine speed at higher engine speed?
I think, Doctor, at higher engine speed.
So that's wrong, ya shabab, because engine has actually higher potential to have engine knocking or self-ignition at lower engine speed. Because ya shabab, the idea here is what? Is to have self-ignition. And to have self-ignition of the fuel, we just need some time. The fuel needs some time in order actually to heat up, and then it can self-ignite. But what happens at higher engine speed? The piston will be moving very fast, and the time actually for each cycle, starting from taking the air until having the exhaust, this time for each cycle will be reduced at higher engine speed. So there is no actually enough time to have the fuel can have actually to self-ignite, and then it can cause knock. So usually engine knocking can be reduced if you raise the speed of your car. So if you have losses in the cooling system or something, and you just want to solve the situation, you can just little bit try to raise the speed of your car. This may reduce the level of noise, because at lower engine speed, the fuel will have the time to self-ignite. And this actually will cause the engine knock, severe engine knock at lower engine speed. But this is not the case. It's not the case in even all situations. In some cases also at higher engine speed, we may have engine knock. So what will happen in this case at higher engine speed? At higher engine speed, we have shorter time actually, as we said, for the cycle. But also we have shorter time in order to have the heat is transferred to the cooling water. So that means at higher engine speed, the heat absorbed by the cooling water will be reduced. And in this case, this will help actually having higher temperature of the end gas region. And it will reduce the time for the fuel to self-ignite. So in this case, the fuel need time to self-ignite, and it will be higher at lower engine speed, but raising the engine speed, it will reduce the time required for the fuel to self-ignite, because the amount of heat absorbed by the cooling water has been reduced. And the gases here in the end region will be actually, the temperature of the gases will be raised in this case. So it depends, shabab, on the engine design in this case. If we have the engine is designed to have higher compression ratio, that means the pressure and temperature at the end of the compression stroke will be higher. And if the engine is running at higher speed, so the time required for self-ignition will be reduced, because the temperature of the end gases has been raised due to the reduction of the heat transfer to the cooling water. That means actually the fuel in this case may result actually in engine knocking at higher engine speed. Okay? But if the engine is designed actually to have lower, little bit lower to moderate compression ratio, that means actually in this case the pressure and temperature will be lower at the end of the compression stroke, and the possibility actually to have knock will be reduced in this case. Okay, so engine knocking can occur at lower temperature. This is actually most probably the case, and also it may or might occur actually also at higher engine speed in this case. Okay, and that's why, shabab, we have to have each fuel has to have actually has to be characterized by its own octane number. Each fuel has to be assigned an octane number value, and this number gives us indication about actually the resistance of the fuel to self-ignite. If the fuel having higher octane number, that means actually this fuel is resisting actually the self-ignition, and it is resisting the knock. In case actually of lower octane number, the case will be just reversed. This fuel actually does not resist actually self-ignition, and it will result actually in engine knock. But how we measure actually the octane number of any fuel? In 1929, this is actually a long time ago, the American Chemical Society for Testing Materials, through actually the Cooperative Fuel Research, we call it the CFR committee, they have developed just a standard test condition on a standard engine. They call this engine the CFR engine. This engine, shabab, is used actually to calculate the octane number for each fuel. And this actually still, this engine, shabab, is used actually for the standard test to calculate the octane number for any fuel, up to date. Okay, So this CFR engine, it consists actually of single cylinder. It is a single cylinder engine. It has the bore or the diameter of the piston is about 3.25 inch, and the stroke also is about 4.5 inch. This engine actually is a 4-stroke engine, and it has variable compression ratio. How we can vary the compression ratio, شباب, of the engine? Compression ratio is mainly function of what? Of the clearance volume. So if we made actually this cylinder head movable, it can move up and down, then in this case by fixing the top dead center, then we can increase or reduce the clearance volume. So this CFR engine is a variable compression ratio. The piston head, the cylinder head actually can be moved up and down in order actually to control the clearance volume, so that actually we can control the value of the compression ratio of this engine. So this engine is a variable compression ratio. It is connected to an electric generator in order to control the running RPM of the shaft, because actually the test to calculate the octane number of any fuel is just actually performed at fixed RPM. Also, Shabab, this engine is connected to a cooling water circuit. We call it actually evaporative cooling. Evaporative cooling, Shabab, that means the cooling fuel actually in the cooling circuit is under the phase change process in order to keep actually isothermal wall condition. So in this case, the cooling water, let's say cooling water at 100 at atmospheric pressure, it should be boiling at 100 degrees C. So the cooling water will be coming at 100 degrees C, so that it will absorb the heat and it will be converted from the liquid phase to the vapor phase. You know, Shabab, while the phase change process, what will happen to the temperature during the phase change?
Again, it was the question.
Sorry?
Can you repeat the question?
During the phase in the CFR engine, Shabab, we have the cooling circuit is evaporative cooling circuit. Evaporative cooling, that means we have a fluid that is actually converted from the liquid phase to the vapor phase. If we have water at 100 degrees C, if we added actually water, let's say water at 30 degrees C, if we added heat to this water, what will happen to the temperature? It will be raised until we reach the saturation temperature, which is 100 degrees C. So what will happen if I continue adding heat at 100 degrees C? Will the temperature of the water be raised?
No, it will be fixed.
No, it will be fixed because we will have some phase change. In this case, we call it this is a latent heat. So the heat added to the water in this case will be just used to convert the phase from the liquid phase to the vapor phase. The idea here, Shabab, in the CFR engine to have evaporative cooling under phase change process in order to keep actually isothermal temperature of the cylinder, of the walls actually of the cylinder. So in this case, we use an evaporative cooling system in the CFR engine in order to keep the wall temperature, the cylinder wall, at fixed temperature. Just we have phase change of the cooling fluid. Type, what are the procedure actually? This is the engine. We call it the CFR engine. But what are the procedure followed actually in order to calculate the octane number of a given fuel? In this case, I will bring this fuel to this engine, and they will be running actually this engine at a given compression ratio. And I will test actually, do you have knocking? No. Then in this case, I will be raising the compression ratio of the engine by reducing the clearance volume. Then I will run the engine at a given condition. Do we have a certain amount of noise? If yes, in this case, we have a decibel meter that measures the amount of noise. Just a simple decibel meter that measures the amount of noise generated by the engine. If it measures a given value at a given compression ratio, that means actually we have knocking of the fuel at this compression ratio. So we will record this compression ratio, and then we will come up actually with two reference fuel, a mixture of isooctane, which is a reference fuel assigned octane number equal to 100. And there is another fuel, we call it actually N-heptane. We assign it actually octane number equal to 0 in this case. And I will bring a mixture of those two fuel. Let's say 90% isooctane, and let's say 10% N-heptane. And I will take this fuel mixture and run the engine using this fuel at the given compression ratio. Do we have the same amount of knocking using the decibel meter? No. That means actually this fuel is resisting the engine knock at this compression ratio. So I will reduce the percentage of the isooctane fuel. So instead of 90%, let's say I will make it 89 or 88, and then we'll have the remaining percentage will be N-heptane. Do we have, and then run the engine? Do we have the same amount of knocking that we have recorded for the test fuel at this compression ratio? If yes, then in this case, actually the octane number of this fuel is represented by the percentage of the isooctane in the fuel mixture of isooctane plus N-heptane that result actually in the same amount of knock at the same compression ratio. Okay, Said, do you have a question?
No, doctor.
So again, يا شباب, the test procedure for any fuel to calculate the octane number, just I will come up with the fuel, test it on the CFR engine, okay, at a given compression ratio, and then measure the amount of noise generated by the engine. If we don't have noise, the required level of noise, then in this case I will be raising the compression ratio until we have a certain amount of knock occur at a given compression ratio of the test fuel. So I will record this compression ratio, and I will run the engine with different mixture of isooctane plus N-heptane that will result actually in the same amount of knock at the same compression ratio. Then in this case, the octane number of the fuel will be represented actually by the percentage of the isooctane in this fuel mixture that resulted in the same amount of knock at the same compression ratio. Okay, those are the test condition under which we calculate the octane number of the given fuel. We have two different test conditions because we have two octane number. We have the research octane number and we have the motored octane number. Research octane number, it has been used originally at the beginning, but they found actually that this research octane number does not correlate well actually with the knocking that occur actually under rear road condition, under wide open throttle, or under full load condition. So they find actually that a fuel have higher research octane number, and it should not result in self-ignition or knocking, but it result actually in knocking. That means actually this octane number is little bit higher. So it does not represent the actual case. That's why they have modified the test in order to have the motored octane number. We call it the motored octane number. So in this test, in case of motored octane number, they try to consider the harsh condition. Like actually here in Saudi Arabia, we have the weather, actually the temperature is high in the summer. So that means the temperature of the air coming into the engine will be higher. And this actually may increase actually the possibility to have self-ignition of the fuel. So this means actually we have to have another test by which we can have actually a reduced octane number, or an octane number actually that is representing the real property of the fuel, that is not affecting actually by the ambient condition. So in the motored octane number, they just try to the intake air temperature from 52 degrees C. They have raised actually to about 150 degrees C. And they have raised actually the temperature, the running RPM of the engine, at which actually the test to calculate the octane number of the fuel has been calculated. It has been raised from 600 RPM. It has been raised actually to 900 in the motored octane number. And also they try to advance the ignition. When we advance the ignition, during the compression stroke little bit early, that means we will initiate the combustion by the spark plug earlier, while the piston is moving up. That means the pressure and the temperature inside the cylinder will be higher in this case. So there is a higher possibility to have self-ignition of the fuel in this case. So just in the motored test, they have advanced the ignition so that actually they can increase the possibility to have self-ignition. Okay, so in the motored test, we have increased the intake temperature, advanced the spark, and we have raised the RPM at which the test has been performed. And this should result in what? The motored octane number should be less or higher than the research octane number. Under this harsh, should be what?
Should be less.
It should be less in this shabab, because we have increased here the possibility of the fuel to have self-ignition, advancing the spark, having higher intake air temperature, raising the RPM, and all of this should result actually in earlier self-ignition and earlier knocking. So the motored octane number should be reduced actually as compared to the research octane number. And the difference give us indication about what, shabab? Yes, Ali?
Didn't you say for that higher RPM will have less chance of having the engine knock?
Yes, but in this case we have advanced little bit the spark, and still شباب 900 RPM is still lower RPM. And as we said, this is mainly function of the engine design. That's why شباب when you run, we cannot calculate the octane number by running any engine. It has to be a standard CFR engine. Okay, I told you self-ignition or knocking can occur at lower RPM or higher RPM, but it depends actually on, let's say here, depends on the engine design. And to calculate the octane number, we have to actually test the fuel on a standard engine, which is actually the CFR engine. We call it the CFR engine. So the engine شباب is already designed to have actually higher possibility actually to have self-ignition or knocking at higher temperature. Okay. So the difference. So yeah, yes, Ali.
Yeah, it's clear. Thank you.
So yeah, شباب, the difference in this case between the research octane number and the motor octane number should give us indication about the sensitivity of the fuel actually to the operating condition. So when we have higher intake air temperature, higher RPM, advancing the spark, so in this case we will have lower octane number. That means the difference between the research octane number and the motor octane number should give us indication about the fuel sensitivity to the operating condition in this case. And the motor octane number should be less than actually the research octane number. But what about the octane numbers that you see in the gas station? Which one is it, the research or the motor? Actually, it is the average value between both of them. So we calculate the research octane number, we calculate the motor octane number, we take the average, and this is actually what we call the anti-knock index, or actually what is common as the fuel octane number. Higher octane number شباب means actually this engine is resisting knocking. Lower octane number mean actually this fuel actually does not much resist the engine knock. So what will happen شباب if we have fuel of higher octane number? That mean actually we have higher resistance to fuel knock, to engine knock. It will have this engine actually, if we have higher octane number, that means the engine can go actually for higher compression ratio. So شباب, usually the engine or the car manufacturer, they wanted to design the engine of higher compression ratio. Why higher compression ratio شباب? In order to have what? To have higher pressure at the end of the compression stroke. So that means higher pressure at the end of the compression stroke. That means we have higher power stroke, and the engine can generate higher power in this case. But usually this high pressure is limited to the self-ignition of the fuel. Okay, but they try actually, the car manufacturer try to design the car for the limiting or the highest possible compression ratio. And that's why they will tell you this car actually is designed to have a fuel of octane number not lower than a given value. When you go to buy actually any car, you will find this car actually is preferred to work with a fuel octane number, let's say 91. And if this car is turbocharged or supercharged, he will tell you that this car cannot work actually for octane number less than 95 to avoid actually the engine knock or the self-ignition of the fuel. Type, this is the case if we have a car that is designed to have higher compression ratio, and that's why it is designed to have fuel of higher octane number. But what about the old car يا شباب? Is it preferred to go to the gasoline station with all the virgin car, and then you just go there and find gasoline 91 and 95, and you say, I will take 95 because it is a better fuel? Is it economically good to do that?
No.
So the answer شباب is no, because in the old virgin car, they are already designed to have little bit lower compression ratio. So that means the pressure and the temperature at the end of the compression stroke will be low. We will not have self-ignition of the fuel. If you use the octane number 91, it will not have self-ignition. And this is شباب a very good fuel, very high purity fuel, 91. So don't use 95 unless your car actually is turbocharged or supercharged, and unless actually the car manufacturer just told you don't use octane number less than 95. So don't go to 95 unless your car actually requires this. Because if you have an older version car, in this case the compression ratio is low, so will not have high pressure and high temperature inside the cylinder, and the fuel will not self-ignite. So it is not good actually to have higher octane number if your car does not actually require this. But having higher octane number, as we said, it will result actually in higher engine power. And some fuel additives, shabab, can be used actually as, but don't do that. Don't try to add methanol or ethanol to your fuel in order, you say this is actually improved the octane number. But as I told you, methanol and ethanol are very bad at the engine cold start. And it may cause actually engine lock, engine vapor lock in this case. Okay, so usually they add the additives very precisely in order to calculate the octane number. So yes, Mustafa?
يس دكتور، لأن هل أقدر أبدل من ال 95 إلى 91؟ Is it
from 95 to 91?
Yes.
If the car actually does not require,
Yes.
the car manufacturer didn't ask you to use 95, so you have to go to 91.
Yes, I know. But يعني إذا مثلا أنا كنت أستخدم ال 95 على سيارات does not need 95. هل أقدر أرجع إلى ال 91؟
Yes, you can do it. This is 95, shabab, is highly pure fuel. And when you get back to 91, you will not have any kind of impurities or soot or something. This is very clean fuel. Also, 91 is a very clean fuel. It's not bad fuel. So when you change from fuel to fuel, this will not actually, you have already upgraded the fuel to 95. This is the case if you have used the lower grade octane number, maybe below 91. So in this case, you may have some soot formation on the spark plug and also in the intake valve. And this may result, shabab, in cleaning. You may require actually cleaning the engine. That's why, shabab, the fuel purity is very important parameter in calculating the engine lock. And from time to time, you will see usually after 100 kilometers of your car, you have to have what we call here, I think they call it تصفية ماكينة. تصفية ماكينة, shabab, that means you have to clean up the fuel injector and the spark plug from the soot, so that actually those soot does not actually act as a secondary source of ignition, because when they get higher, they will self-ignite the fuel. So we have to clean it. We have to make تصفية ماكينة. So in this case, even in some severe situation, we have to change the spark plug, and also we have to change actually the fuel injector, and we have to clean up the intake valve as well to remove the soot and all the accumulation, so that we can prevent the engine locking in this case. Okay. طيب, what about this area, shabab, the case of liquid fuel? Liquid fuel are characterized by the octane number. طيب, what about the gaseous fuel like methane? In this case, there is a number which is called the methane number. And in the same CFR test, we can calculate actually the methane number for any gaseous fuel. We test the gaseous fuel until it actually results a certain amount of knock at a given compression ratio. Then we record this compression ratio, and we come up with a mixture of methane plus hydrogen. Then we change the composition of methane plus hydrogen until we get the same amount of knock at the same compression ratio. Then in this case, the methane number will be represented by the percentage of methane in the fuel mixture that result actually in the same amount of knock at the same compression ratio. Usually, shabab, we have some fuel with methane number, some gaseous fuel with methane number higher than 100. So in this case, instead of using a mixture of methane to hydrogen plus hydrogen to calculate actually the methane number of the fuel, they use actually a mixture of methane plus carbon dioxide. And they measure the amount of engine knock at the same compression ratio for the test fuel, and then they calculate the methane number to be equal to 100 plus the percentage of the carbon dioxide by volume in the mixture of methane plus carbon dioxide. And this is a shabab for the gaseous fuel. So for the liquid fuel, we have the octane number that give us indication about the resistance to self-ignition. In case of gaseous fuel, as I told you, nowadays actually there is a trend to convert the car to work using natural gas, which is mainly methane. So in this case, we have to have, instead of actually octane number, we have to have the methane number in this case. And as the methane number increase, that means actually the fuel is resisting self-ignition. But we said self-ignition occurs actually in a spark ignition engine. But can it occur actually in diesel engine? Can we have knocking in diesel engine? So we said knocking, ya shabab, is what? Knocking is exactly heterogeneous combustion. We have combustion at different location inside the combustion chamber. So successive self-ignition will result in engine knocking. But in case of normal combustion, we have just the combustion is initiated by the spark plug, and it is spread inside the cylinder until it burns all of the fuel. But in case of knocking, we have heterogeneous combustion. We have combustion at different locations. And this one what result actually in engine knock. That can we have heterogeneous combustion in case of diesel engine? Can we have it? So yes, shabab, we can have self or heterogeneous combustion and it may cause engine knock. Yani this is actually a very rare case to happen, but it may happen if we have longer ignition delay period. Ignition delay period is the period from the start of injection of the fuel close to the end of the compression stroke until the initiation of the combustion, until the combustion starts. So we inject the fuel, then the fuel actually mixes rapidly with air, then it self-ignite in one shot, self-ignition. But if actually it is lower grade fuel, when we inject the fuel, it will be injected inside the cylinder and it will take time to self-ignite. This time, shabab, the fuel will spread inside the cylinder and it will be mixing with air with different concentration. Then in this case, when the pressure and temperature is raised, in this case, the combustion will not be initiated at the same time. We will have several combustion zones in this case. And this may cause actually the engine knock. So the engine knocking in diesel engine occurs when we have actually longer ignition delay period. So the fuel is injected, but it takes actually longer time in order to self-ignite in this case. And that's why, shabab, as we said, the fuel property is the most important one in order to calculate for the gasoline engine in order actually to resist the self-ignition. The fuel property is the most important actually parameter in controlling the self-ignition inside the cylinder. And to improve actually the octane number of the fuel, we have to have some additives. Like, as I said, like additive to improve the octane number, like actually biomethanol from biosources, or ethanol, or tertiary butyl alcohol, or we can have methyl tertiary butyl alcohol. All of these are additives in order to improve the octane number of the fuel in order to resist the self-ignition. Also, we add some fuel additive like detergent in order to clean up the fuel injector and the deposit. You can see here, shabab, if we have some deposit in the intake valve even. So in this case, at the engine cold start, this will act like a sponge. It will absorb the fuel injected to the cylinder, and it will result actually in very poor cold start of the engine. Also, at higher load, if we have severe accumulation on the intake valve, it will reduce actually the intake area of the char, and it will reduce the amount of fuel to the cylinder and at higher load condition. So this will result actually in reduction of the engine pump. And that's why we have to have some detergents to be added to the fuel in order to clean up the fuel injector. Also, we have to add in some cases, we add some corrosion inhibitor and antioxidant in order actually to prevent the gum formation in the fuel tank. And we may have some oxygenated fuel, as we said, like methanol or ethanol. It has to be added actually to the fuel in order to improve the octane number. If we have some liquid water in the fuel, shabab, this may result actually in severe effect on the fuel nozzle, in the fuel injection nozzle, in the fuel injector. And that's why in some cases we have to add some acetone if the fuel actually is having some amount of water in order to absorb the water from the fuel. Type, this is regarding shabab, the gasoline engine, and it is characterized by the fuel octane number. Higher octane number will actually result in resistance to the self-ignition and resistance to engine knock. Lower octane number means the fuel is not resisting self-ignition. But what about the diesel fuel? The most important property, shabab, for the diesel fuel is the fuel viscosity. Because the diesel fuel, as we said, the injection system in the diesel engine is completely depending on the fuel injection pump. So the whole injection system is represented by the fuel injection pump. So the fuel in this case has two functions. Is to generate actually to be the energy source in order to run the engine, burn the fuel and run the engine. And it has also another job, which is lubricating actually of the injection system, the lubrication of the fuel pump and the lubrication actually of the fuel injector. So there is two functions of the diesel fuel: the lubrication to lubricate the injection system, and also to act as the energy source to be burned to generate heat inside the combustion chamber. Then we can generate the engine pump. So if we have this fuel is a very low viscosity, that means actually the fuel effectiveness as a fuel lubricant will be reduced in this case, because it is very light liquid. It cannot absorb heat or act as a lubrication in this case. And on the opposite, actually, if we have higher viscosity, the fuel is of higher viscosity. In this case, the fuel will be injected actually in big droplets. It cannot mix easily actually with the air inside the combustion chamber, and it will result actually in higher ignition delay. Higher ignition delay period, that means we may have actually a possibility to have actually engine knock in the diesel engine. So if we have lower viscosity, the fuel does not act well as a lubricant. If we have higher viscosity, that means the amount of meter the fuel will be reduced to the engine, because actually the fuel is resisting to the flow movement. And in this case, the fuel will be injected in big droplet, and it will not mix fast with the air, and it will result in longer ignition delay, and it may result actually in engine knocking in the diesel engine in this case. So we should have actually the fluid should be actually of a moderate or proper viscosity, so that actually it acts as a lubricant as well as acting actually as the energy source for the engine. Also, having lower viscosity, shabab, that means we will have a smaller fuel droplet that will be mixing rapidly with the air inside the cylinder, and will have actually in this case excessive heat release and excessive temperature and pressure rise inside the cylinder if the fuel viscosity is very low. But if the fuel viscosity is very high, so we'll have large droplet that will evaporate actually and burn very slowly, and in this case it may result actually in longer ignition delay, and in this case most probably the fuel will not complete the combustion, and in this case it will result actually in more emission of the engine in this case. Okay. Type another property which is very important in addition to the viscosity for the diesel fuel is the engine the fuel bore point. Bore point, shabab, is the minimum temperature at which the fuel can flow through the filter and the fuel pump. If the fuel is existing at temperature lower than the bore point, it will be so difficult actually to be pumped through the fuel pump, and it cannot move through actually the fuel filter. And in the cold countries like Canada or something, the temperature of the fuel in the fuel tank should be above the bore point by 5 to 8 degrees C, so that actually the fuel can flow easily through the fuel pump and it can be injected through the fuel injector. If the temperature of the diesel fuel is less than the bore point, that means actually the fuel cannot flow through the fuel filter and it cannot be injected through the fuel injection pump. But how we can calculate the bore point of the fuel, of a diesel fuel? In this case, we just bring a fuel jar, just a tube, we just fill it with the diesel fuel, and then we can cool it down, reduce its temperature, until actually when we move it from the vertical position, from the vertical position to the horizontal situation, it will not result actually in movement of the fuel within 5 seconds. So we just cool down the fuel in the test jar slowly, and we reduce the temperature. Then we move every time. We just flip the tube from the vertical situation to the horizontal situation. Is there a movement of the fuel within 5 seconds? If we don't have a movement of the fuel within 5 seconds, so this is actually, this temperature is representing the bore point temperature, which is the temperature at which the movement of the fuel is very slowly and it cannot be injected through the fuel injector in this case. Okay. The most important property of the diesel engine or for the diesel fuel is the cetane number. In case of gasoline engine, we have the octane number, which gives us indication about the resistance of the fuel to have self-ignition. Here, actually, shabab, the opposite case is the cetane number for the diesel fuel. It gives us indication about the ability of the fuel to self-ignite faster. So that means, shabab, the fuel of higher cetane number, that means it should be what? Of lower octane number. So we cannot use the diesel fuel for the gasoline engine, because in the diesel fuel, the fuel should be of higher cetane number. That means the fuel actually is able to self-ignite very fast. So if we use the diesel fuel in a gasoline engine, that means actually the fuel will self-ignite very fast, and it will cause actually severe engine knock in this case. Okay? So the cetane number is totally opposite to the octane number of the fuel. The fuel يا شباب of higher cetane number, we just need the diesel fuel to just ignite very fast. Even يا شباب while the injection of the fuel at the end of the compression stroke, while the fuel is injected, the fuel actually should be initiating the combustion, even while the injection, not after the injection. Once we initiate the injection, the fuel will start the combustion in this case. And in this case, we will not have engine knocking in this case. Usually the cetane number of the diesel fuel, for gasoline it is octane number, it is 91, 95 as we said, but in case of diesel the cetane number is ranging from 40 to 55. This is actually higher quality diesel fuel. Also in case of diesel fuel you may have some additives. In this case we add some nitrate ester in order to improve actually the cetane number. But you can imagine if we improve the cetane number by let's say 10 units, we have raised the cetane number from let's say 40 to 50, this will result actually in significant drop in engine emission. Diesel engine is characterized by having higher emission compared to the gasoline engine. Okay, diesel fuel, it depends on self-ignition, and actually this needs time to self-ignite and to complete the combustion, and usually it results in incomplete combustion, the diesel fuel. So that actually it can result also in higher emission compared to the gasoline engine. Also diesel fuel is a heavier fuel. It has higher amount of carbon in the fuel in this case. And this will result actually in another kind of emission like the particulate matter and the soot. This is actually the characteristics of the diesel engine. So usually diesel engine are characterized by higher emission compared to the gasoline engine. And this is another reason that diesel engine are not actually spread in different uses actually like the gasoline engine, because gasoline engine can run at higher engine speed and also they have lower emission compared to the diesel fuel. However, the diesel engine have higher efficiency. It is efficient more than actually the case of gasoline engine, because diesel engine can run at higher compression ratio in this case. By increasing the cetane number of the fuel by 10 units, let's say from 40 to 50, it will result actually in emission reduction about 80% of unburned hydrocarbon and about 50% reduction in the carbon monoxide due to the incomplete combustion of the fuel. The carbon monoxide emission will be reduced about 50% if we raise the cetane number by 10 units, and also for the particulate matter, it will be reduced by about 30% in this case. So the cetane number is a very important parameter for the characteristics actually of the diesel fuel. Type how we can calculate the cetane number? Typically, it is the same CFR engine, but it is a diesel engine in this case. We use this engine at a given operating condition. This is the intake air temperature 66, the cooling water temperature at 100 degrees C. So most probably this is a water under atmospheric temperature, under phase change, evaporative cooling, in order to keep the temperature of the wall fixed while the cooling process. The engine RPM is 900 revolution per minute, and the fuel injection starts 13 degrees before the top dead center. And the injection pressure is about 103 bar, which is actually the injection pressure in diesel engine is much higher in order to make sure that the fuel will be evaporated very fast and it will mix and start the combustion very fast in case of the diesel engine. Type the CFR engine will be running the engine for a given fuel that we need to calculate the cetane number until actually we have an ignition delay period equal to 30 degrees C. Ignition delay شباب is the period from the start of injection to the start of combustion. In this case, in this test, we start inject the fuel 13 degrees before the top dead center. So if we need to have ignition delay period of 13 degrees, that means actually the start of combustion should occur when the piston is at the top dead center. So we will be running the engine using the test fuel until we have ignition delay period of 13 degrees C. So we start to inject the fuel 13 degrees before the top dead center. That means the fuel, if we have ignition delay of 13 degrees, that means the fuel will start the combustion when the piston is at the top dead center. And we will be recording this compression ratio, at which we have ignition delay of 13 degrees. Then we will have the reference fuel. In case of gasoline engine, شباب, we have isooctane plus N-heptane as the reference fuel. Isooctane having octane number of 100, N-heptane have actually octane number of equal to 0. And based on that, we calculate the octane number. Here in diesel engine, we have two reference fuel. We have hexadecane, which has cetane number equal to 100, and we have heptamethyl-nonane, which has actually cetane number equal to 15 in this case. Then we get a mixture of this fuel, let's say 90% and 10%, or 80% and 20%, and then start testing this fuel in this engine. Does it result in the same ignition delay period? If yes, that means actually this composition of the fuel is representing the cetane number of the test fuel. If not, then in this case we'll be repeating the test until we have the mixture of hexadecane, we call it cetane, plus heptamethyl-nonane that represent actually have the same ignition delay period at the same compression ratio. That means the fuel cetane number will equal to the percentage of hexadecane, or the percentage of the cetane fuel, plus 0.15 multiplied by the percentage actually of the heptamethyl-nonane of the fuel. And that should be representing the cetane number of the fuel. Earlier, when they start actually the early stage of calculating the cetane number of the fuel, they used actually, instead of heptamethyl-nonane, they have assigned actually another fuel which is methyl-naphthalene. Methyl-naphthalene was assigned a cetane number equal to 0. So in this case, the cetane number will equal to the percentage of the cetane fuel in the test mixture. But later on, they have replaced actually the methyl-naphthalene by the heptamethyl-nonane, as actually the heptamethyl-nonane is little bit better fuel. It has cetane number equal to 15, and it is actually less expensive fuel, and also it does not result actually, it has actually a better storage characteristics in the fuel tank. So in this case, they preferred actually to use the heptamethyl-nonane instead of methyl-naphthalene. And based on that, we calculate the cetane number of the fuel. Heptamethyl-nonane, شباب, hepta prefix mean we have 7 carbon atoms. Heptamethyl, that mean we have 7 methyl group attached to the nonane. Non means the prefix of 9, means actually we have 9 carbon atoms. So this is the nonane of 9 carbon atom, but we have heptamethyl group are actually attached to the methyl-nonane in this case. And this is an isomer actually, شباب, of what we call the heptamethyl-nonane fuel, okay, or what we call actually the cetane. This is an isomer of the cetane fuel. We call it heptamethyl-nonane. Is that clear, شباب? Abdullah, Abdul Muhsin? Is that clear, شباب? So it is the same CFR engine, but we just change the reference fuel, and in this case we calculate the fuel that will result in the same ignition delay period, and based on that we can calculate the cetane number of the fuel. As I told you, شباب, gasoline fuel is a poor diesel engine fuel. So if we try to use a gasoline fuel of higher octane number, that means it is resisting self-ignition. If I used it in a diesel engine, it will be actually of lower cetane number, and that means actually the fuel will be resisting self-ignition. And vice versa, if we use the diesel fuel in gasoline engine. If you look here, شباب, the fuel of higher octane number, here, fuel of higher octane number, that means the fuel is of lower cetane number. So if I use the octane number, let's say of 95, like in case of gasoline engine, if I used it in the diesel engine, it will be about having a kind of 5 cetane number. 5 cetane numbers, that means the fuel actually is resisting self-ignition. So when I inject it in the diesel engine, it will not result actually in fast self-ignition, and it will result in engine. And also the case is reversing. If we have a diesel fuel of higher cetane number, let's say 100, that means actually it will be actually a very low octane number in this case. So we cannot use the diesel fuel for the gasoline engine, and also we cannot actually use the gasoline fuel for a diesel engine.